So now we will talk about hierarchical clustering, which is another different way for doing some clustering. So basically, we saw k-means, which is possibly the most widely used, EM, which is a generalization of k-means. So it's getting to something more general and more, I would say, coherent with parametric methods and probabilistic modeling. Now we go with something quite different, which is hierarchical clustering. So the idea is that we can make this kind of heuristic approach. There are different ways of doing it. We can see this as, I would say, an iterative data agglomeration approach. So when we are making, we are getting data put together. So we start with all data being a group. So we just say, okay, one sample is one group. So we have n samples and group, and then we combine them by fusing the groups. So we are merging the two most similar groups and recalculate the mean center of these fused groups. That means that we will iterate about n-1 times from n groups to one group. And we will, at each step, merge two groups together to create a bigger group. And this is repeated on just sequentially. So this is kind of straightforward. And in fact, hierarchical clustering dates from the 70s or even before. So it's relatively simple. We also have the opposite approach. In opposition to data agglomeration, we have the data splitting division approach, where we start with one group. So basically, we say everything is in one group, and then we look at splitting, dividing the group in two different, and we have some criterion to say, okay, this is the right way to split. So we need to get some approaches to some heuristics that are making the split. And we are repeating this until n groups are obtained. So it's kind of bottom up versus top down. Bottom up is more the agglomerative. We just say we start with everything as a group, if we sample as a group, and we just merge it until one big group. And the data division is the opposite. We just start with one big group and we split it until we reach n different groups, one per data. And for achieving this, we need to get some kind of similarity measurements between groups, not just between single samples. So this is a little more tricky, but we can use things like single linkage clustering. So basically, we are looking at all the pairs of sample between two groups. So we have the group G1 and GI and GJ. So we say every combination of one sample from GI with one sample from GJ, what is the distance? And we are taking the minimum distance among all these distances between one sample of each group. And this gives us the single linkage clustering distance for the distance between these two groups. And we have the opposite approach, where we are looking, in fact, at the maximum value of this distance between each pair from one compared to the other. So like a sample from group I compared to a sample of group J, and doing this for all pairs of samples from I and J, and using the maximum value. So something, an illustration of that, because it is kind of straightforward. We have here 6 samples, A, B, C, D, E, F. And with the plot on the left it is really just the plane in 2D where they are positioned. So we don't have anything more fancy than that. So these are 2D data. And we are using Euclidean distance here between the samples. So we see that, for example, between A and B, the distance is 1. Between B and D, the distance is square root of 2, and so on. And between E and F, it is distance of 2. So we have these distances. And now if we apply hierarchical clustering here, agglomerative approach, basically looking at single linkage, so basically the minimum distance between samples from one group to another, we have these results on the right. So basically the results on the right, we should maybe look at from the right to the left, because it's, I would say, a way to see it. So we have all the letters here, which are corresponding to one sample here. So A, B, C, D, E, F. And we are looking at our group. And what we see is that, okay, and on the x-axis also, it's the distance between these groups. So we can see here at first that everything at distance 0, there's, I would say, 6 groups, 1 per sample. But we can see that at distance of 1, there's something that is going on. In fact, the samples A and B are merged, and the samples D and F are merged at distance 1. And that makes sense. You know, AB is at distance 1 and DF is at distance 1. So these two are merged at the same distance. So this is at the distance 1. So this is where they are. So these are the two first groups created. So we go from 6 to 4 groups in one shot because they are merged simultaneously parallel. And then the next step is to say, okay, the next merge will be done at square root of 2 here, which is 1.4 something. So this is a distance where group, I would say AB, which are already merged, and the group DF, which are already merged, are then merged through the diagonal between B and D. So this is at a distance of square root of 2. So this is the one that expresses that link here. And likewise, we have a link between C and E at this point. This is the tribe here, where we have a distance of square root of 2. And finally, we will merge everything into one single group through the distance between E and F, which is the smallest one, which is equal to 2. So this is the distance we are using to merge everything together. So the group CE with the rest, A, B, D, F. So this is basically how it works. And the point is, hierarchical clustering is that it's not the most performing approach. In terms of clustering performance, it's not particularly good. In fact, it's relatively poor, but not poor, but I would say far from what we can get, for example, with k-means. But in terms of visualization, in terms of some ways of processing the data it provides, it can be quite useful, and it is still used for different purposes, including the visualization. Because the nice thing with visualization is that, contrary to k-means, we don't have to set the value of k. We just have every clustering from n to 1 directly, and we see how they are merging. And this view here, this diagram is called a dendrogram, the dendrogram view, which is basically a tree that is turned on one side, that is giving us the merging of all these samples. It is super helpful to understand the relation between the data and to see how the clustering is done. So I would say in general, clustering use is has many purposes. We can make use of clustering for exploring some data structures. We want to see the structure in some data sets, and making use of clustering, it is possible to make it because we don't need labels. We just need to put the data and try to see which group are there, or how similar they are. And so we can organize them into similar groups. We can just use clustering to define the Korean groups and try to synthesize them with one sample or some descriptive statistics over that group, and avoid you looking at the single samples, looking more at the group characterization. And also experts can name these groups according to the concepts they represent. A concept can be represented by different groups, but we can still capture that. So we can say, okay, yeah, the concept of letter A, can be this capital letter, these small letters, this typographic character, for example. And how do we classify the at, this one out? Maybe we should represent it in some way because that's A, but not exactly, whatever. So we can have different groups to represent the different groups to represent one concept. It's also quite useful for data preprocessing. We can look at the value in the HI space. We can rely on this value of clustering to feed a classifier, for example, or we can project, we can make a discrimination in that space according to the assignment that is made to the different groups. And we can also use that to, in fact, evaluate mixture density. So we can use this in mixture models. We can use this to evaluate distribution of classes made of several groups somehow. So this will be done that way. An issue with clustering is to choose the right number of groups. So the right number of groups is kind of crucial. For example, with k-means or EM. So the question is how to determine it. I mean, what is the best approach for determining the groups? Some application impose it naturally. For example, with the color map, we are looking for exactly k equal to 256 groups. So this is the number of colors we're looking for. So we don't choose anything. We just set it at 256 and try to find the best color map for that. We can also maybe just plot it in 2D using PCA and looking at the results, or maybe TSCE also. And from that, we can see the number of natural groups that are emerging from that and use that as a guide to do the clustering. There are some incremental algorithms that can be used to dynamically add centers or according to some criteria. And we can basically also ask experts to verify, to validate that the groups that we are relying are making sense. Maybe possibly by looking at images, by analyzing the prototypes, the centers of these groups, we can validate with the experts that this makes sense. This is a group that is meaningful in terms of the context we are working on.